All right, so we are going to finish up the chapter with volume. It also brings us to the end of the book. But volume, first part of that goes over units of volume. One thing to keep in mind is volume is now three-dimensional. 3 dimensions, it's 3D. So when we look at volume, we can think of kind of like length, width, and height. Sometimes you think of it as length, width, and depth, but it's 3D. So you're not just on an XY plane, you're now on an XYZ plane. So 3 dimensions that we're looking at. And the first part is converting English units to volume or metric to volume, but as we already did that with area and doing the conversion, it's the same concept, only you're going out to centimeters cubed, feet cubed, yards cubed. So I'll leave that for you to take a look at, as we've already done it with 2 dimensions, so just extrapolate out to 3 dimensions, same idea. What we do want to look at today, though, is the volume of a prism. Okay, prisms and cylinders. Not cylinders, we just did that. Sorry, pyramids. And this is actually a lesson that I really enjoy doing with my students because you can do a lot of visuals and you can get really creative with this. So let's first start with volume of a prism. Now, remember when we talked about prisms in the past, prisms maintain their shape throughout the solid. They maintain their shape. So each slice is the same shape. So you can get very creative with some manipulatives, and so that again, they could memorize a formula, but we can get really creative. So today we can look at a standard deck of cards, because a card, you know, if I give you a single card, we know what that shape is. That shape's a rectangle. But then if I stack another one and another one and another one and another one and another one, you get the idea. I end up with this solid deck of cards. So it's kind of fun to use some household items. So I grabbed some cards, I grabbed some crackers, because oftentimes you might have, these are just stackables, you might have some crackers where every single shape is exactly the same, and yet when you stack them, you end up with a solid cylinder. So that prism is going to keep its shape all the way through it. What else? Similar type thing. I grabbed a coaster. And then a second coaster of the same shape. A third coaster of the same shape. So when you look at them from above, all you see are a lot of circles. But when you turn it over, you'll see that you have this stack of circles however high that you're going. I would have grabbed the loaf of bread, but my son had several sandwiches at lunch. But you get the idea. A loaf of bread has the exact same shape throughout. All right, so, and I didn't want to open the crackers and get crumbs everywhere. All right, so let's take a look at how we find volumes of various solids, because that's what this comes down to. Volume is a solid. So what else did I use here? I used coasters, bread, a loaf of bread. And so those are nice visuals for students to see that when you stack them all individually, you end up with a solid shape. Okay? So in my opinion, the easiest way to think of volume is think of the area of the base because that's going to give you your rectangle if you're talking about cards, or perhaps your circles if you're talking about crackers. So you need the area of one of them, and then simply multiply it by however high that stack is. And then we'll talk about pyramids in a moment. All right, let's first do some of these solids. So, and we need to remember that whenever we're talking about height in comparison, that the height always needs to be perpendicular. It needs to be at a right angle. We're not talking about the oblique shapes. We're talking about where height is perpendicular to our base. So oftentimes you might see this represented as a capital B to represent the area of the base times the height. Okay? And then volume is 3 dimensions. So let's start with, let's think about this for a second. I thought I wrote down, I did. All right, so let's start with our deck of cards. So a fun activity to do with students is give them a deck of cards, if they're allowed to have cards, and let's figure out the volume of this prism. So here we go. Find the volume of a standard deck of cards. I.e., this is going to be a rectangular prism. A prism maintains its shape. What shape is it maintaining over and over and over again? Well, it's a rectangular of that one card. So if I want to look at this, okay, I have my rectangular prism, and it's just a stack of cards. So I could draw a picture as well. I could start with rectangular, and it's going to be however deep these cards are going to go. Okay, so perhaps I have this sort of sitting like this. Right, it's kind of hard for you guys to see. I have to put this down. Okay, and having measured this a few minutes ago, your standard deck of cards, if I round it to make the numbers a little bit nicer, are 9 centimeters long by 6.5 centimeters wide. So that's one rectangle. And then if I stack them on top of each other, for ease, it comes out about 2 centimeters high if I stack up that entire deck. And so I know a lot of times students just memorize length times width times height. Well, I'd rather think of it as volume equals the area of the base, because we can use any shape, times the height, as long as the base and the height are perpendicular. So in this case, this is the area of a rectangle times the height. So the area of the rectangle would be 9 centimeters by 6.5 centimeters, not meters. Wow, that would have been quite interesting. Times the height of 2 centimeters. And actually, that was a great mistake I made, because we need to make sure the units of measure are all the same. So if one unit is different, we need to do the conversions that we did earlier in the chapter. And so now this becomes a multiplication problem. And 9 times 6.5, we get 58.5 centimeters times centimeters is centimeters squared, times our height of 2 centimeters, leaves us with a volume of 117 centimeters to the third power, which we needed it to be 3-dimensional, because remember we are talking about it's now length, width, height, x, y, z plane. Okay, so that's pretty much just your standard deck of cards, and it's a nice way to show them that it's just one card stacked on top, on top, on top. So similar idea, let's do our crackers. because I like this because it's a different shape. So what they need to do is identify what shape is being repeated and stacked over and over and over again. So you could either draw it so that it is vertical, or you could draw one that is lying on its side. So if I look at the volume of a cylinder, now you could memorize, but why? When in doubt, just write out what we know. So the volume is the area of the base times the height, as long as the base and the height are at right angles to each other, they're perpendicular. Well, for your information, it's pretty much a name brand cracker. You know, these come in stacks. And I'm going to just tell you offhand, one of these crackers, okay, one of these crackers, the diameter is about 50 centimeters. Scratch that. 50 millimeters, or about 2 inches. And just for your information, the height of one cracker, if I were to measure one cracker, is about 5 millimeters. So I needed to make sure the units of measure were the same. So I went with millimeters. All right, so if we were to do this volume of stackers, then I'm going to look at, I know what one cracker is. I know this is a cylinder. I now have been given some dimensions based on the manufacturer that says this diameter is about 50 millimeters. Okay. One cracker is 5 millimeters high, but I'm going to go, if I count them, I'm going to end up with 14 crackers in one stack. Okay, so I end up with 14 crackers high. Each cracker is 5 millimeters. All right, so now that we know how high it is, now that we know what the diameter is, since we know what the diameter is, we also know then that the radius is only 25 millimeters. So we now have all our parts and pieces. Let's put them together to find the volume. So our volume is going to be the area of the base. Well, the base is a circle. Circle has a radius of 25. So we have pi r squared times our height. So this is pi times 25 millimeters squared times our height. Well, we have 14 crackers, each one's 5 millimeters high. So that's 14 times 5 millimeters. 25 squared, 25 times 25 is 625 pi millimeters squared. 14 times 5, okay, 14 times 5 is 70 millimeters. So our total volume of this stack of crackers is 43,750 pi millimeters cubed, because we had the area on the bottom times the height. Okay? So this will work with any shape as long as we know what the shape of the base is. So instead of memorizing a whole lot of formulas, we just use the area formulas that we've already done. Okay. So I do not have with me, unfortunately, a trapezoidal prism, but we're going to do one anyway. because all we need is the area of the base times the height. So let's take a look at a trapezoidal prism. So let's practice drawing that first. Let's find the volume of a trapezoidal prism. So a trapezoid, remember, has a quadrilateral. It's got 4 sides. 2 sides are parallel but not congruent, and we will head this off in this direction. Okay. Bring that down, bring that down, bring that back across. And for ease, we'll give you some numbers that will work out rather nicely. So one of the bases of the trapezoid is 20 meters. The other base, which is the other parallel side, is 16 meters. The depth, or how far back we're going to go with this trapezoid, is 10 meters. And the height, which is always measured perpendicular, those 2 bases, I'm going to call that height 5 meters. Okay. So, and then we need to remember how to find the area of a trapezoid. Okay, so remembering the area of a trapezoid, we know volume is simply area of the base, or the shape that is staying throughout the entire prism. So in this case, it's a trapezoid, times the height, or how far back we're going to take that trapezoid. So the area of a trapezoid, we've already covered that. That's 1/2 the height of the trapezoid times the sum of the bases. And in this case, I don't want to necessarily use the word height twice. So I'm going to refer to the height as the trapezoid, and then I'll multiply it by the depth, or how far back we go. And the rest is substitution. The height of our trapezoid is 5 meters. The 2 bases, the 2 parallel sides, are 20 meters and 16 meters. And the depth, 10 meters. So 20 and 16, 36 meters times 10 meters. And since it's volume, remember we're looking at 3 dimensions, we should end up with a cubic power. So if we multiply this all out, we should end up with 900 meters cubed, right? So volume is really quite nice when you break it down into all the single components. So if we have a prism and that shape stays the same throughout the whole thing, find the shape of that, the area of that one base, and just stack them up. Okay. Now we need to take a look at pyramids. And with pyramids, you can think of it as they come to a point. So with a pyramid, and I've got some, here we go. So these are all going to have an apex that they all come to, whether it's a pyramid with a circular base, square base, triangular base. So the key is with that pyramid, I could have, let's do this. Let's do a pyramid with a square base. So there's the apex. Or we could have a pyramid with a triangular base. Here's the apex. Or we could have a pyramid with a circular base, which we usually call a cone. Okay. Any way we look at it, these all come to a point, that apex point. So our volume I can't really say the shape of the base times the height because, as you know, if I have a pyramid, it's not the same shape all the way through. It's getting smaller each time we go to the top. So in this case, we're going to take 1/3 the area of the base times the height. And the height and the base, again, have to be perpendicular to each other. And this lesson's pretty fun to demonstrate, because one way you can demonstrate, oftentimes you're like, well, why is it 1/3 of it? Well, one of the best ways to demonstrate this is show them. So what I did was, I've got our shapes that we've used in the past, and I took shapes that had the same base. So if I look at my prism, I look at my rectangular prism, or my cube actually, I grabbed the cube. You'll notice that the base on the cube is the same as the base on this pyramid. So they actually line up perfectly. And the height of the cube is the same as the height of this pyramid. So the bases have the same shape, so the area of the base is the same. The height's the same, but it should look like this pyramid is smaller than this cube. And so a nice way to show it is, because we want to know it's 1/3, so I'm going to show that it's going to take 3 pyramids to equal 1 cube. So what I'm going to do is actually grab some water and take this water and color it so that it's easier to see. Okay. We just made that purple. That's pretty well mixed up. And I'm going to take my pyramid that has the same size base as this cube, and I could show you, it's harder to see on camera, but this will fit inside here, so you can see that the height of the pyramid's the same as the height of the cube. And then just demonstrate, I'm going to put it in here so we don't splash, that if I take my pyramid and I fill it up, 1, pour it into the cube, 2 times, 3 times, and I can't quite get all the way to the top. Okay. You'll notice that had I been able to get all the way to the very, very, very tippy top, that it would fill up this cube. I don't think I can show you sideways. It fills the cube up almost to the very top. So it's a really nice way to show that. And students sometimes go, yeah, I don't believe you. Do it again. So I'm going to grab a different set of shapes. Again, here's a cylinder. So the cylinder has a base of a circle. So I'm going to take a pyramid, also known as a cone, that has the same size base, which is a circle. So I can show you that they're the same base. They match up perfectly. If I put them next to each other, their heights are the same. Or you can show them that the heights are the same by putting the cone inside the cylinder. Okay? There's a little lip on this for demonstration purposes, so it may not fit exactly. And again, it should take 3 cylinders to fill, 3 cones to fill up this 1 cylinder. So it's a fun one in class to do. Just grab a bright color. One. 2. Whoops, that's why I have the bowl there. And sure enough, 3 of the cones filled up 1 cylinder. Again, it's kind of hard for me to show you. I can't turn on its side. All right. So that helps with the students to visually, instead of them just trusting and memorizing a formula, you can show them how that volume is affected by having it simply come to an apex. Okay? And then last but not least, I would show you the same, one more demonstration, if it's a prism that has a triangular base going to a pyramid that has a triangular base. Again, they match up. However, there's a crack in our pyramid, so hopefully you just trust me on that one. But I think you get the idea there. And then the last is volume of a sphere. So in this case, think of our sphere. Easiest way to draw it, we got our circle, and then we practiced this a little while ago with surface area. We can go around this way to demonstrate the depth in the back, and then we can do the same thing coming forward to show that it's coming out at you. And there's our center. So it should look like a 3D sphere or a ball. And this volume is 4/3 pi r cubed. All right. So, for example, if we want to take the, let's find the volume of a sphere having a radius of 9 millimeters. So at this point, we pretty much are showing, just show how we've got that. Always start with your given, always start with what you know. Have them always start with what we know. 4/3 pi r cubed. Well, in this case, our only unknown is the radius, which we've been given. So our volume is 4/3 pi, make sure they keep the unit of measure in there, 9 millimeters, and that entire unit is being cubed. So we end up with a 4/3 pi, 9 times 9 times 9 is 729 millimeters cubed. A little reducing, 4 times 729 divided by 3 should give us 972 pi millimeters to the third power. And again, make sure your units of measure match. So volume's 3D, so we need to make sure it's third degree. And guys, that pretty much is it. That takes us to the end of the chapter, which takes us to the end of the course. So hopefully that was helpful. And until next time.